Welcome to Topictrick. I'm excited to bring you another episode in our DB2 Complete Reference Series. Today, we're diving deep into one of the most critical aspects of database performance, DB2 memory structures. Whether you're a computer science student just starting your database journey, a fresh graduate preparing for your first database role, or an experienced professional looking to sharpen your DB2 skills, this video will give you the foundational knowledge you need to understand how DB2 manages memory and why it's absolutely crucial for performance. By the end of the session, you'll understand exactly how DB2's memory architecture works, why proper memory management can make or break your database performance, and how to apply these concepts in real-world scenarios. Let's get started. Think of DB2's memory architecture as a well-organized warehouse system. Just like a warehouse has different sections for different types of goods, DB2 uses specialized memory pools to handle different types of database operations. But here's the key insight. These aren't just random storage areas. Each memory pool is carefully designed for specific tasks, and they all work together like a perfectly choreographed team. DB2 uses these specialized memory pools to minimize one of the biggest performance killers in any database system, disk input-output operations. Remember, accessing data from memory is lightning fast, while reading from disk is painfully slow in comparison. The beauty of DB2's approach is that each memory pool acts as a dedicated workspace. Buffer pools handled data pages, EDM pools managed compiled code, RID pools optimize complex queries, and thread memory ensures smooth concurrent operations. Understanding this architecture isn't just academic knowledge, it's the foundation for making smart decisions about database tuning, capacity planning, and troubleshooting performance issues in production environments. Let's start with the star of the show, buffer pools. If DB2's memory architecture is a warehouse, then buffer pools are the main storage floor where all the action happens. Here's how it works in practice. When your application requests data, DB2 doesn't immediately run to the disk. Instead, it first checks the buffer pool, which acts as a high-speed cache between your application and the physical storage. If the data is already in the buffer pool, congratulations, you get lightning-fast access without any disk operations. This is called a buffer pool hit, and it's exactly what we want to happen as often as possible. But if the data isn't in the buffer pool, that's a buffer pool miss. DB2 has to read from the slower disk storage, but here's the smart part. It stores that data in the buffer pool for future use, so the next time someone needs that same data, it's ready and waiting in memory. The size and configuration of your buffer pools directly determine how often you get those fast memory hits versus slow disk reads. This is why buffer pool tuning is often the first place database administrators look when optimizing performance. Now, let's talk numbers, because the performance difference is absolutely staggering. Look at this comparison between memory access and disk access times. Memory access from a buffer pool takes about 10 nanoseconds. That's incredibly fast. But disk access? That takes about 10 milliseconds. Let me put that in perspective. Memory access is literally 1 million times faster than disk access. 1 million times. If memory access was like walking across a room in 1 second, disk access would be like taking an 11-day journey. This is why we obsess over buffer pool hit ratios. In a well-tuned DB2 system, you want to see buffer pool hit ratios of 95% or higher. That means 95% of your data requests are served from fast memory, and only 5% require slow disk access. When buffer pools are too small, you get more cache misses, which means more disk I/O, which means slower query response times and reduced overall throughput. It's a direct, measurable impact on your application's performance. For database professionals, understanding this relationship helps you make informed decisions about memory allocation and explains why adding more memory to buffer pools is often the most cost-effective performance improvement you can make. Next, let's explore the EDM pool, which stands for Event Database Monitor Pool. This is where DB2 stores its compiled SQL statements and executable packages. Think about what happens when you run a SQL query. DB2 doesn't just execute it immediately. First, it has to parse the SQL, check the syntax, optimize the execution plan, and compile it into executable code. This compilation process takes time and CPU resources. Now, imagine if DB2 had to do this compilation every single time you ran the same query. That would be incredibly wasteful, especially for applications that run the same queries repeatedly. This is where the EDM pool shines. After DB2 compiles a SQL statement for the first time, it stores the compiled version in the EDM pool. The next time you run that exact same query, DB2 can skip the entire compilation process and reuse the pre-compiled version. This reuse capability provides massive performance benefits. You eliminate the CPU overhead of parsing and optimization, and you get much faster query execution times for frequently used statements. The EDM pool is particularly important in OLTP environments, where applications tend to execute the same SQL statements over and over again. Proper EDM pool sizing ensures that your most frequently used compiled statements stay in memory and don't get aged out. Now let's discuss the RID pool, which handles row identity processing. This might sound technical, but it's actually solving a very practical problem in query optimization. When DB2 processes complex queries that involve multiple indexes, it needs a smart way to combine the results from different index scans before accessing the actual data pages. Here's a real-world scenario. Imagine you're searching for customers who live in California and have purchased products in the last 30 days. DB2 might use one index to find California customers and another index to find recent purchasers. The RID pool temporarily stores the row identifiers from both index scans. DB2 can then sort and merge these row identifiers, eliminate duplicates, and organize them efficiently before accessing the actual data pages. This process dramatically reduces random I/O operations because DB2 can access data pages in a more sequential, organized manner. The size of your RID pool affects the optimizer's ability to choose efficient access paths for complex queries. If the RID pool is too small, the optimizer might be forced to choose less efficient execution plans, which impacts query performance. Understanding RID pool behavior helps you troubleshoot why certain complex queries might not be performing as expected, especially those involving multiple index lookups. Let's shift our focus to thread memory management, which is all about supporting concurrent database connections efficiently. In DB2, each thread represents an individual database connection or work unit, whether it's a user running a report, an application inserting data, or a batch job processing transactions. Each of these activities requires its own thread with dedicated memory allocation. Thread memory serves several critical functions. It stores the connection state, manages temporary data during query execution, handles intermediate results, and maintains session-specific information. Here's why this matters for capacity planning. If each thread requires a certain amount of memory, and you need to support 1,000 concurrent users, you can calculate your total thread memory requirements. Understanding these requirements helps you plan for peak usage periods and avoid memory-related bottlenecks. Poor thread memory management can create performance bottlenecks during high concurrency periods. If threads don't have enough memory, they might have to use slower temporary storage, which impacts response times for all users. For database professionals, thread memory concepts are essential for understanding system capacity limits and planning for growth in user populations or application workloads. DB2's workload management takes memory optimization to the next level by recognizing that different types of database work have different memory requirements and characteristics. Let's compare two common workload types. Reporting workloads typically involve complex analytical queries that scan large amounts of data. These workloads benefit from larger buffer pools because they're reading lots of data pages. They also need increased sort memory for aggregation and ordering operations, and they can tolerate longer execution times in exchange for thoroughness. On the other hand, Transaction processing workloads focus on high concurrency with many small, fast operations. These workloads need optimized thread memory allocation to support many concurrent connections efficiently. They require fast response times and effective lock management to minimize contention between concurrent transactions. DB2's workload management allows you to allocate memory resources based on these different characteristics. You might configure larger buffer pools for your reporting environment while optimizing thread memory for your transaction processing system. This workload-aware approach ensures that each type of database work gets the memory resources it needs to perform optimally, rather than using a one-size-fits-all approach that might not be ideal for any particular workload. Let's examine how memory utilization directly impacts database performance with some concrete metrics. This performance curve shows what happens as your memory pools approach their capacity limits. When memory utilization is optimal, you get excellent response times and high throughput. But as utilization increases beyond 90%, performance starts to degrade. At 95% memory capacity, response times begin to increase noticeably as the system struggles to find available memory for new operations. At 98% capacity, performance degrades significantly because the system is constantly managing memory pressure. When memory pools exceed their capacity, performance can collapse dramatically. Response times skyrocket as the system is forced to use slower alternatives like temporary disk storage, and throughput plummets as operations queue up waiting for memory resources. The key insight here is that memory allocation decisions have direct, measurable impacts on application performance. Insufficient buffer pool memory leads to excessive disk I/O. Inadequate EDM pool space causes unnecessary SQL recompilation. Poor thread memory management creates bottlenecks during peak usage. This is why proactive memory management is so critical. You want to monitor utilization trends and adjust allocations before you hit these performance cliff edges, not after your users start complaining about slow response times. Now, let's step back and see how all these memory components work together as an integrated system. This is where the real magic of DB2's architecture becomes apparent. The memory hierarchy shows how different components complement each other. Buffer pools provide the primary data caching layer, ensuring fast access to frequently used data pages. EDM pools optimize the query processing pipeline by reusing compiled SQL statements and execution plans. RID pools enhance complex query performance by efficiently managing index operations and reducing random I/O patterns. Thread management ensures that each connection has the resources it needs without interfering with other concurrent operations. But here's the crucial point. These components don't work in isolation. They're designed to work together synergistically. A well-optimized buffer pool reduces disk I/O, which frees up system resources for other operations. Efficient EDM pool usage reduces CPU overhead, leaving more processing power for actual data operations. When you're tuning a DB2 system, you can't just focus on one memory pool in isolation. You need to consider how changes to one component affect the others. For example, increasing buffer pool sizes might reduce the need for large RID pools, or optimizing EDM pool usage might allow you to allocate more memory to buffer pools. This integrated approach is what separates good database performance from exceptional database performance. Let's talk about practical best practices that you can apply in real-world DB2 environments. First, and most importantly, monitor memory utilization regularly. Use DB2's built-in monitoring tools and system views to track buffer pool hit ratios, EDM pool usage, and thread memory consumption. Set up alerts for when utilization approaches critical thresholds. Second, balance pool sizes based on actual workload patterns, not theoretical guidelines. Every environment is different. A data warehouse will have different memory requirements than an OLTP system. Use your monitoring data to understand your specific usage patterns. Third, adjust configurations dynamically based on performance metrics. DB2 provides tools for online memory reconfiguration, so you can tune memory allocations without downtime. Don't set memory configurations once and forget about them. Fourth, always consider trade-offs between different memory allocations. Memory is a finite resource, so allocating more to buffer pools means less available for other components. Use performance data to guide these decisions. Fifth, implement regular maintenance procedures that include reviewing and tuning memory settings based on changing workloads. As your applications evolve and data volumes grow, your memory requirements will change too. Finally, be proactive about preventing bottlenecks. It's much easier to prevent memory-related performance problems than to fix them after they impact production systems. Let's wrap up with the key concepts you should remember from today's session. First, understand the core memory components. Buffer pools provide fast data access and are often your biggest performance lever. EDM pools store compiled SQL for efficient reuse, eliminating redundant compilation overhead. RID pools optimize complex index operations and reduce I/O randomness. Thread memory supports concurrent connections and scales with your user population. Second, remember that these components work as an integrated system. You can't optimize one component in isolation. Changes to buffer pool sizes affect other memory requirements. EDM pool efficiency impacts overall CPU utilization. Thread memory allocation affects your concurrency capacity. Third, recognize the dramatic performance impact of proper memory management. Memory access is literally 1 million times faster than disk access. Proper sizing directly affects query performance and system throughput. Configuration decisions have measurable impacts on application response times. Finally, follow proven best practices. Monitor utilization regularly using DB2's built-in tools. Balance pools based on your specific workload patterns, not generic recommendations. Consider trade-offs when making memory allocation decisions, and maintain a proactive approach to memory management. Mastering these concepts is essential for maintaining high-performance DB2 environments and optimizing database operations for your specific requirements. That concludes our deep dive into DB2 memory structures. I hope this session has given you a solid foundation for understanding how DB2 manages memory and why it's so critical for database performance. Remember, this video is part of our comprehensive DB2 Complete Reference Series here on Topictrick. We're building a complete learning path that covers everything from basic concepts to advanced administration and performance tuning. If you found this content valuable, please hit that subscribe button and ring the notification bell so you don't miss any videos in this series. We have many more DB2 topics coming up, including indexing strategies, query optimization, backup and recovery, and advanced administration techniques. Drop a comment below if you have specific DB2 topics you'd like us to cover, or if you have questions about anything we discussed today. I read every comment and use your feedback to plan future content. Thanks for watching Topictrick, and I'll see you in the next video where we'll be exploring DB2 indexing strategies and how they work with the memory structures we discussed today. Until next time, keep learning and keep growing your database skills.